All right, we've been looking at dissolving a solid into water, and that's how we're looking at our reactions. The solid dissolves into its ions, and will it dissolve depend on the KSP value. Let's look at it from the other way. What happens if you add two solutions together that have soluble ionic compounds, but the product is insoluble according to our GenChem 1 solubility rules? Will a precipitate occur like GenChem 1 says? What does KSP have to say about this? Well, let's take a look. So if we add, say, 100 milliliters of zero point 0.1 molar sodium chloride to 100 milliliters of zero point 0.1 molar silver nitrate, what will happen? Well, our GenChem 1 brain will say, well, we know sodium chloride, aqueous. Our solubility rules say that this dissociates 100% into its ions. Silver nitrate also dissociates 100% into its ions. We do a double displacement reaction, and we will get sodium nitrate. Our solubility rule says that is completely soluble, dissociates 100% into its ions, plus silver chloride, which is not soluble, should form a solid. That's what GenChem 1 says. Let's check that with KSP. Something to note, the KSP equation tells you the concentrations needed for a saturated solution. Remember, the KSP has always got the solid in equilibrium with the ions in solution, and that means it's a saturated solution. You have to have that amount of ion, that concentration of ion, to have solid in there also. And so what we're going to do is calculate the QSP, just as in an equilibrium chapter, just where KSP, QSP is the same equation. It's just QSP if we're not sure we're at equilibrium. Now, here's the thing to remember here. This is the reaction we ran up here, the sodium chloride and the silver nitrate in solution to produce a silver chloride. Here is that net ionic equation. But if we're looking at KSP and QSP, note that that equation is not the net ionic equation. It's actually the reverse of the net ionic equation. The KSP and the QSP equations are the solid in equilibrium with the ions in solution, the opposite of our net ionic equation from up here, which was the ions going to the solid. So make sure you got that right. When you're calculating KSP and QSP, make sure it's the solid dissociating into its ions. Right, because we know if our QSP is too large, then we have too much product, which means we'd have too much ions in solution, and the reaction would go back to the left to form solid, which means we would get a precipitate. Now, the first thing we need to do with our problem up here is realize that we mixed 100 milliliters of this solution with 100 milliliters of this solution, so our volume of solution is 200 milliliters now. Our concentration, if we went from 100 milliliters of 0 0.1 molar to 200 milliliters, that means our concentration is going to go down to 0.05, and this is just a quick M1V1, M2V2 calculation for that. So we know when we're calculating our QSP that our concentration of silver is going to be 0.05 molar, concentration of chloride also 0.05 molar. And so we plug those values into our QSP equation as if all ions were in solution. We're going to say, okay, we dumped the ions together before any reaction happened. We had 0.05 molar silver ion, 0.05 molar chloride ion. Do the math, and we get 2.5 times 10 to the minus third is our QSP. Recall our KSP for silver chloride, because it's this reaction here, the silver chloride dissolving into silver plus chloride. Our KSP for silver chloride is times 10 to the minus 10th. Therefore, this is QSP is much larger than KSP, which means the reaction will go to the reverse, will go to the left to form more product, to form solid, which means, yes, we will get a precipitate if this occurs. All right. So here's another question, though. What if we add same reaction, 100 milliliters of 1 times 10 to the minus 5th molar sodium chloride with 100 milliliters times 10 to the minus 5th molar silver nitrate? Will silver chloride form? And our GenChem 1 brain will say, well, yes, because we've got our silver, we've got our silver here, we've got our chloride here, we're doing the same reaction as up here. Yes, we will form a precipitate. Well, let's calculate the QSP. Here, our concentration of ions are so small that QSP is 2.5 times 10 to the minus 11th, which is smaller than the KSP, of 1.77 times 10 to the minus 10th. Therefore, you will not get a precipitate. This solution of sodium chloride and this solution of silver nitrate are so not concentrated, they're so weak in ions that there's not enough ions present in solution to form silver chloride solid according to the equilibrium KSP. So here's a situation where no, you do not get a precipitate form, even though your equation says you should. A precipitate will not form due to such low concentration of initial ions. They are not there in an amount large enough to get a precipitate. All right. And whenever we get information like that, we can always use that information for good or for evil. Let's use it for good, shall we? Let's look at selective precipitation, something that happens actually quite a bit in chemistry. So here's the deal. You have a solution that has both calcium ions and magnesium 2+ ions, and you need to separate the ions from each other. But they're both in solution. So how do you separate them from each other? Well, if you look at tables of solubility, you would find that calcium hydroxide has a KSP of 4.68 times 10 to the minus 6. Magnesium hydroxide has a KSP of 2 times 10 to the minus 13th. Since they're both calcium and 2 hydroxides, magnesium and 2 hydroxides, both 3 ions, then our KSPs are going to tell us that magnesium hydroxide is much more insoluble than calcium hydroxide. You can get more calcium hydroxide dissolved in water than magnesium hydroxide. Since magnesium hydroxide is less soluble, perhaps we could just add a little bit of hydroxide, enough to get the magnesium hydroxide to precipitate out, but not enough to get the calcium hydroxide. Well, the question is, how much hydroxide do we need to add in order to get this done? In order to get magnesium hydroxide to precipitate, but not the calcium hydroxide? Well, our KSPs will tell us. All right, so let's start with our magnesium hydroxide. And we say, all right, we have magnesium hydroxide in equilibrium with Mg2 plus and 2OH minus. This is just the KSP equation for magnesium hydroxide. We need to do an ice table because we know we're starting out with 0.1 molar calcium hydroxide and 0.1 molar magnesium hydroxide. That's what I set up in this problem. So if we got 0.1 molar of each solution, we need to set up the ice table because recall this is a solid, therefore it's not in there, but our initial concentration of magnesium is 0.1 molar. We don't have any hydroxide. When this dissociates according to KSP, we get X and 2X, 0.1 plus X and 2X here. Plug in our KSP value for magnesium hydroxide, do our math, and we find the concentration of hydroxide is 2X, which is 1.44 times 10 to the minus 6th molar. What that means is, if the concentration of magnesium is 0.1 molar and the concentration of hydroxide is 1.44 times 10 to the minus 6 molar, we have a saturated solution and no magnesium hydroxide will precipitate. We'll just have a saturated solution. However, we add just a little bit more hydroxide than this, and magnesium hydroxide will start precipitating. So we know our concentration of hydroxide has to be larger than 1.44 times 10 to the minus 6 molar. If our concentration of hydroxide is less than this, then we don't have a saturated solution. No magnesium hydroxide will precipitate. But as long as we bump that concentration larger than this, we can get magnesium hydroxide precipitating out. But we have to be careful because we don't want any of the calcium hydroxide to crash out of solution to precipitate out. So we need to calculate, okay, we need at least this much, but we got to make sure we're lower than the amount needed for the calcium. So let us calculate how much calcium or how much hydroxide is needed to precipitate out calcium hydroxide, make sure we're below that amount. And we do the same with the nice table. We're starting with 0.1 molar calcium, 0 hydroxide, X2X. We have a different KSP value now. Do our math, and we find out our concentration of hydroxide at which calcium hydroxide will start precipitating is 6.0 6.84 times 10 to the minus third molar. All right. And so note what we have here. As long as our concentration of hydroxide is below 6.84 times 10 to the minus third molar, then no calcium hydroxide will precipitate out. But our concentration of hydroxide has to be above 1.44 times 10 to the minus 6 molar. And due to Le Chatelier's principle, we want to get as much hydroxide as possible to make sure we shift this equilibrium as far to the left as possible to precipitate our magnesium, which means we want to add a little bit less than 6.84 times 10 to the minus third molar. Say 5 times 10 to the minus third molar, maybe as low as 1 times 10 to the minus third molar. A larger concentration of hydroxide than this up here, so magnesium will precipitate out. A smaller concentration of hydroxide needed for calcium to precipitate out, but close to that amount so we can get the maximum amount of magnesium precipitating out. And that's how you do a selective precipitation problem. All right. We're over 10 minutes with this video, so I'm going to stop it here, and we will finish up the chapter in a slightly shorter video next time, where we're going to look mainly at complex ion equilibria.